Hey, we're back. We've been on a bit of a break. We've been super busy and been away from our projects, but we are back. Whilst we were away, we finished our claw machine Gantry robot, and this is it, finally working, as you can see. We did this project because we wanted to start applying the knowledge we learned from our ongoing robotics degrees.
We've learned a lot from this project, and it's given us a chance to hone a lot of our skills, as well as learn some lessons that theory just can't teach you. Whilst we could just keep changing and improving on bits of this, we feel like we've got it to a reasonable state to call it completed. And so for now, we're going to call it finished and move on to a new project, as we've got a lot of other things that we want to work on. In this video, we're going to cover the build of this claw machine from start to finish.
If you have seen some of our previous videos on this, then some of this might be duplicated, but we would really appreciate some feedback on this new video format, so let us know what you think. We started this project in around February and spent vaguely one day a week on it. Our main objectives were to find a way of applying some of the theory that we were learning and to actually just build something. The key things we wanted to improve on were CAD, electronics and programming. We decided to build a robot for no real reason other than it felt like a reasonable thing to do whilst we were doing a robotics course. We started by looking online for robot arms and projects that people had already done for some inspiration, and we ended up finding a robot arm project on Thingiverse where the original project included machine vision and motion control. However, the problem was that a lot of the information was missing due to the website no longer being live, so we had to resort to going on the Internet Archive to find some information.
Thankfully for us, the 3D CAD files were still available, which was very useful. However, 90% of the assembly instructions for the arm were unavailable, which meant we kind of had to jumble our way through putting the whole thing together. We also decided to not attempt the machine vision aspects at this point and keep the project scope small enough to be achievable. We would like to do some machine vision in the future, but it was just too much to roll into this project. We did, however, want to build a custom controller so that the Gantry robot could be used like a claw machine.
Simply put, a robot arm is just a series of links, or bones, and motors, or joints. Our robot is just two links with two rotating joints on a platform mounted to a belt-driven gantry.
We're lucky enough to have a friend over at RI Print Hub, which is a printing company in the UK, and they printed the parts for us on really short notice with a really quick turnaround. We'll put a link to their website in the description below in case you want some printing doing. The parts were printed in PLA, and we did them in multiple colours just to make it easier for us to distinguish them apart when we were working on the assembly, as we only had partial instructions.
We used 25 kilogram servos, which are probably overkill, but it's what we had access to. With the robot built and the motors in place, we could start to work out the working envelope of the robot. Servos can move through 180 degrees, but the robot itself can't without tearing itself apart, so we started a fairly arduous process of finding the physical limits of the robot. Because we are broke students and we didn't want to have to buy replacement parts, we spent a lot of time finding the safe working angles of the robot and hard coding limits into our script to protect the robot. First, Seb would set the first joint angle, and then he would turn a potentiometer to set the second joint angle to the safe minimum and maximum, determined visually. These angles would be displayed in the Arduino IDE serial monitor, which I would then write down in one big table.
From analysing the safe limits of the robot, we wrote a quick script to plot its workspace, which is essentially everywhere it can safely reach, and we then ran the robot through those trajectories in a loop and were just about able to overlay the plot onto the actual recording of the robot moving, which was quite cool. It was slightly janky because of the perspectives of the camera, but it was still really interesting for us to see this and see how simulation can sometimes marry up to reality. Up to this point, we hadn't actually started working on the gantry, or the linear axis, as the sliding rails are surprisingly expensive, and we had plenty to get on with the first iteration of the robot, just getting it moving and controlled. To start doing controls, we built a rudimentary controller. It was very basic and used two linear potentiometers from an old amplifier and a dial for the end effector. With this, we could move the motors manually and get the robot moving through its workable space, even picking things up. It's kind of amazing how much pride one can feel for getting something working when it's so trivial. We're feeling quite enthusiastic by this point and very motivated, and decided to start working on the next big integration, the gantry.
We had a stepper motor from an old Ender 3 3D printer and figured it made sense to use that for the gantry. It allows precise control and variable speed, And this is where things started to get gnarly. Finding any kind of documentation for the stepper motor was such a pain, let alone finding documentation in English. But after a fair amount of digging, we did find a single page that showed the pinouts and the sequences, and we can link that in the description too, for anyone trying to use one of these steppers.
By trade, I'm a carpenter, so it made sense to knock a quick frame up out of wood. And then we found a file for mounting a stepper that we could adjust to attach it onto one side of the rail. The other end we did with the same mounting plate and added a reducing flange that we designed and printed. We then bought a 5 meter length belt that came with spindles, which we cut down and assembled. We designed a second controller board at this point to include the gantry movement and printed that, and just about got the whole thing working by the end of our university semester. We had managed to maintain 1 day a week on this project up to this point, whilst also doing exam revision and coursework, and everything had been going well. It was now the summer, and we were thinking that we would have more time to spend on the robot and easily be able to finish this project in no time.
As is always the case, our uneventful summer went absolutely mad. Seb ended up getting a job that took him all around the country for months, as well as spending a lot of time away due to family illness, and I was meant to start a placement year that subsequently fell through, and then ended up in hospital for a week, with a 2-month recovery. But after all that, we regrouped halfway through the September, having not managed to find a single day for these projects. It took us a little bit to get back into the swing of things, but once we knew what we had to do, we put our heads down. What was left was the CAD for the cases and a new controller, alongside some smarter solution for the circuitry. As up to this point, the robot had been running off of breadboards, which was a total mess.
For circuitry, we decided to use stripboard. It's readily available, and we didn't want to design and order a batch of PCBs when we only really needed one custom board, so we got to assembling. We wanted to use RJ45 Ethernet connectors for connecting the various cases. Ethernet cables are readily available and means the whole system can be taken apart easily if we want to move it. We broke the circuitry into 3 key components: the motherboard, which is the brains of the operation and contains the Arduino, motor driver and power input; the motor box, which handles power and signal distribution to the motors and sits on top of the gantry; and finally the controller, which runs from the 5 volts from the Arduino and uses joysticks as inputs. I'm just going to talk briefly about this controller, which is the 3rd or 4th controller that we've tried to use for this project, and this is where we're up to in the development of a sort of complete controller for any project. We've got standard Arduino thumbsticks with push buttons, as well as some extra push buttons along the top here, and this is on a standard Ethernet port again, and we're going to try and make that interchangeable across all of the controllers that we use on projects. We started developing this after we did the footage for the gantry robot, but you literally unplug the other controller, plug this one in, and then good to go. It's quite small, it's actually very small for me, and there's a few things that need changing on it. We just need to sort of expand everything out in all directions, and then it's kind of good to go. Obviously it's bolted together at the moment, but we can trim those back. But once we've got a working version of this, or like a comfortable version of this, we will publish this, because it's quite hard to we found it quite hard to find controllers that were usable for this project. You can find CAD files or sort of 3D scans of PlayStation controllers or other controllers like that, but realistically you can't like build standard components into those. Everything for that is totally custom. So once we've got a working version of this, we will publish it, and you will be able to find it and use it, download it, print it, do whatever you like. So that's the final note from me. I'll see you later.
So we got to assembling everything, putting it all in place and connecting it all up, and there were some very weird problems.
Yeah, the Ethernet ports that we're using are incredibly noisy, but only sometimes and seemingly randomly. We couldn't find a reason behind the noise. The power supply has a minimum draw threshold to work, otherwise it just switches on and off. The servos seem to randomly reset themselves to home from time to time, and we eventually found out that we blew the small servo on the end effector and had to replace that. And we'd miswired the cables coming over the Ethernet cable. But eventually we got it all sorted, and we switched from linear potentiometers to joysticks and set around changing the code.
Where the potentiometers directly set the position of the motors, the joysticks couldn't really work like that, as they are very sensitive and much less range of travel, meaning if you move them just a fraction, you're trying to push the motor a long way through its range of motion. This meant that with the same code, using the joystick caused the robot to fling back to the middle over and over again when you released it, which caused many problems. The fix for this was to convert the control from position to velocity, which we set to trigger at a certain threshold. And once we had done this, we were finally done.
We have learned so much throughout the course of this project, from CAD to code. We've had to source parts for which we didn't know the name, find ways of powering 4 different motors at 3 different voltages with 1 power supply, troubleshoot control loops and work out some pretty janky ways to time things. But overall, it's been a really fun project and given us a good baseline of knowledge for the next one.
If you ever had an issue driving a stepper from an Arduino, just know that the serial monitor runs too slowly for the stepper to be controlled at the same time. So if you're getting wacky behaviour, stop sending things to the serial monitor.
There are a few things we would do differently if we were to do this project again, or if we were to continue working on it, but we're choosing not to do that. However, we will outline some of the improvements.
Our velocity-driven control works on a threshold value, meaning the motor either moving or not moving, depending on the joystick position. This can lead to some pretty abrupt acceleration, so it theoretically has infinite acceleration in those threshold instances, meaning it can end up launching whatever it's holding. We would resolve this with some smoothing function in there to add a bit of a curve to the acceleration.
We would also change our power supply if we were to do this again, to use a more generic socket. We had a 9V 2.5 amp supply lying around, and we used that because it works, not because it was the right design choice, but that could definitely be improved on.
We do still intend to work out the kinematics for this robot and integrate a switch onto the controller to allow you to move from joint space to Cartesian space for control. We haven't got around to that yet, and for now this is functional enough to form a rather unintuitive claw machine.
One major thing that we really should have done differently is check the reach of the robot before building the wooden frame, and I'll take responsibility for that. I kind of eyeballed it, thinking that it didn't really matter, and it means we've had to put anything we want to pick up on raised platforms for the robot to be able to reach them.
At the end of the day, we wanted to learn from this process and prove to ourselves that we could actually build a system, and we did it.
Our next project is going to be much more intentional. We're planning it in an entirely different manner and intend to break it into a series of concise modules that make sense each on their own, which can then be assembled into the whole.
Thank you for spending the time to watch this, and if you made it to the end, let us know what you think of the style of this video. Have a lovely day, and we'll see you soon. Peace.